Hey guys, today we're going to finish up with Einstein's theory of relativity and the weirdness that goes with that. Last time we talked about the twins paradox and focused mainly on time dilation and how time is affected on objects that we see that are going really fast. But what we'll see today is that it's not just time that changes when we observe things that are going very, very quickly. So I'm going to go through a few of these. And then I'm going to have, it's only going to take a couple of minutes. Then I'm going to have you watch a video that kind of summarizes all of this stuff, starting with Einstein's idea of the speed of light being constant and going through all of the stuff that I'm going to preview right now. Now, it's kind of an interesting video. The animation is kind of odd, and the music is genuinely spacey. So it's kind of a strange video, but it's good in the sense that it goes over everything in a sensible, understandable manner. Now, as you watch it, it's going to seem like it's going along kind of slowly, going through one thing and another, which most of which will be fairly familiar to you. And then all of a sudden it gets to kind of the end of what we have covered and it starts talking about the things that I'm previewing today, other effects. And then it seems to go kind of fast. So that's why I'm previewing it. So you have a little idea of what's coming here. Okay, so the first thing of effects of Einstein's relativity is what we've already seen, that as we watch objects approach the speed of light, time on that object slows down. So when we look through the window of a spaceship going by really fast, we see their clocks moving more slowly than our own. We've already talked about that. Other effects are that the length of the object gets shorter. So if we watched a spaceship go by really, really fast, it would appear to be shorter to us than it appears to be to the passengers on board. Um, Let me show you what that looks like. This one here. Okay, so um, the rocket's going by towing the banner, and at 10% the speed of light, it looks pretty much like it looks to us every day. If it's going 86.5% the speed of light, which is obviously faster, the thing has gotten shorter. At 99% of the speed of light, it's gotten a lot shorter. And at 99.99 the speed of light, it's so short that it's almost not even there anymore. Now, notice it only gets shorter in the direction that it is traveling. Its width does not change. So from in these images here, from top to bottom of each banner, that does not change. It's only the length of the object and the direction which it's going, which is very strange, but hey, that's how it is. So length changes. It gets shorter. And as weird as it sounds, as it seems, if I go back to that animation here, if to the pilot of the spaceship going by, the pilot of the rocket going by, it's the world outside that seems to get shorter. So each side, each object sees the other one getting shorter. They'll talk about that in the video. Okay, what else? Now, another thing that happens is that the mass of the object increases. Again, this is an object that we watch going by that's going really, really fast. To us, its mass has increased. So these rocket ships that are going by towing the banners, they don't all have the same mass. The one with the least mass, the lightest one, is the one up here at the top. And then as they get shorter lengthwise, their mass goes up. And it actually goes up quite a bit. And the faster it goes, the heavier they get. And the video explains why this is. It does it in terms of momentum and beach balls bouncing off of each other. So keep an eye out for that one. You might want to watch that little part a couple times because it's kind of strange. It makes sense when you think about it. You have to understand the concept of momentum for that one, but we've covered that, and most of you know what momentum is. Okay, now this idea that the mass of the object increases as it speeds up led Einstein to his famous equation, E equals mc squared. And what this equation says is that energy and mass can be converted from one to the other. So the E in this is energy in joules, and the M in it is mass in kilograms. And C is the speed of light, and you actually have to square that number. That's the speed of light in meters per second. So 300 million meters per second is how fast light goes, which is pretty fast to start with. But then we have to square that number. So C squared is 90 with 15 zeros out of it after it, or 9 with 16 zeros after it. That's a really, really big number. And what this means is that if you take an enormous amount of energy and somehow condense it, it will kind of pop out as a piece of as a chunk of matter. And conversely, you can take a piece of matter, and if you can somehow disassemble it, it would just erupt into an enormous amount of energy. Now, these numbers are too big for us to wrap our heads around, but um, just for perspective, the atomic bomb that was dropped on Hiroshima in World War II converted about 1 gram, 1/1000th of a kilogram, 1 gram of matter into pure energy. That's about as much matter as in the last joint of your little finger, about 1 gram. That much mass turned into energy was enough to wipe out an entire city. So, yeah, this equation tells us that there are almost unimaginable quantities of energy locked up in matter. Um, yeah, so now that's enough to get us going here on the video. So um, you can stop this one and watch the video. It's the second one that's on the assignment sheet there. It's about 16 minutes long. I hope you enjoy it. It's kind of strange and interesting. And when you're done, then we'll come back here and we've got a little bit more for you. But